Alright, let's get this going. It's day 96 of 100 Days of ML. Previously, I planned to do multimodal models today. However, I'm going to push that to tomorrow. And what I'm going to do is continue semi-supervised learning, but more focused on the co-training algorithm. Day 96. So I'll make this day 97. Here's what we're gonna do. We're gonna first revise semi-supervised learning with this paper that I found from the CMU notes, Semi-Supervised Learning in Encyclopedia of Machine Learning. Then continue with the main paper for the co-training algorithm, combining labeled and unlabeled data with co-training, the paper by Tom Mitchell. After that, if we have time, I'm going to continue with transductive inference for text classification and using SVMs. It's not really related to co-training, it's an alternative algorithm for semi-supervised learning. But I just want to have an understanding of just not just co-training, but other algorithms as well, just to know what the general functionality of SSL is. Okay. Let's go ahead and start with this paper then. From labeled and unlabeled data, transductive learning. Uses both labeled and unlabeled data to perform supervised learning or unsupervised learning tasks. But there is some sort of distinction between inductive SSL and transductive learning. Inductive, the learner has both labeled and unlabeled training data. So where Y represents the label, X is the independent variable. And here x of I is just the production of some function of x, the predictor. Okay. Where f is a function, f is a subset of capital F, where this is the hypothesis space. Okay, yeah. Here, small x is the subset of x, which is input instance, and y is the target label. P of x comma y, the unknown joint distribution, and P of x is it's marginal. and typically L is a lot less than U. Right, so that just means that there's more unlabeled data than there is labeled training data. Learn a predictor that predicts future test data better than predictor learned from labeled training data alone. Okay, transductive. So this was inductive. We have both labeled training and unlabeled data. So in transductive, the setting is the same except one is solely interested in making predictions on the unlabeled data. Here, do we make predictions on both? Inductive learning learner has both as a predictor. So there's a joint distribution and a P of X. So P of X comma Y and P of X. And here, let's see, in transductive, one is solely interested in predictions on the unlabeled training data without any intention to generalize to future test data. Interesting. In the latter case, an unsupervised learning is enhanced by labeled data. Semi-supervised clustering. Dimensionality reduction, one might have the target low dimensional coordinates on few instances. So we're going to be focusing on the former case, learning of a predictor, P of X and P of X comma Y, and somehow using both of these values to learn the model, teach the model to learn versus just using non-labeled training data. Read that theory. What implicit ordering is induced by unlabeled data, and how the algorithmic how to find an algorithmic predictor near the top of this implicit ordering and fits the labeled data well. Okay, we have some generative model here with some probability. Y, conditional of theta. What is theta? Multinomial over Y. Parameters of the joint probability. A predictor f of theta Getting a little lost here. They're using logarithmic for likelihood. So this was for what? I don't know, just theory, I guess. Semi-supervised support vector machines. Something I can skip. Graph-based models. I need to read this. Multiple different trainers. Learners trained on the same level of data. Where each web page, okay, so take the example of web page classification, where each web page X is represented by two subsets of the features of or views. X1 can represent the words on the page itself, and X2 could X2 the words on the hyperlinks. The page is pointing to this page. Okay. Co-training trains two predictors, f of 1 on x of 1 and f of 2 on x of 2, but initially from the labeled data. This is kind of what we looked at yesterday with the CMU lecture slides. But it's written in a more formal format. If f of 1 confidently predicts the labeled of an unlabeled instance x, then the instance label pair x comma f of x of 1 is added to f of 2's labeled training data, and vice versa. This promotes both of them to predict on the same x. Repeats so that they teach each other. Multiview models can be generalized to use more than two predictors. The disagreement of a tuple and label data can be defined as summation of unlabeled and summation of labeled. I'm assuming this is unlabeled because it's L and plus U. I'm not sure what the M is here. C is a loss function. So we're taking the loss of f of u and f of v. And that could be defined as like 1 to m or whatever, how many ever predictors we have. And x of I, both the same inputs, okay. Typical choices of C are the 1-0 loss for classification and the squared loss for regression. Disagreement induces an implicit ordering on the tuple from small to large. And predictors to be of diverse types. Okay. And then we can minimize the loss to get to optimize it. Yeah, that's interesting. I think I got a pretty good description of the algorithm. I wonder why this paper is so long then. PAC Learning in large input spaces. OT Learning. Graph representation. What is PAC Learning? I think I saw it somewhere here as well. Hmm. Okay, I think they're just examples. Most of the definition happens here in section 2. It's probably the same as this, whatever, condensed description happened here. I want to look into deep learning co-training models. There's a lot for vision, but there's not anything for, oh, right here, sentiment classification. download the PDF. I guess methods exist. I don't really want to read this paper right now for applying code training in deep learning. I definitely need to check it out. I mean, if that's possible, one transition could be figuring out how to use code training with deep learning and introducing a paper in that direction. Otherwise, like, I'm not sure because I'm going to be working on research for this. I'm trying to figure out what area requires like assistance. And the co-training model is like very specifically described and could be implemented, but no official implementation is introduced using like any sort of programming languages in these papers. They give results. That's great, but there's no code. So one thing we could do is reproduce the code for this, but that's just reproducing the work. There has to be some sort of new novel addition to make a paper out of it. I don't know how we could improve the model. That's going to be pretty hard work. What we could do is, I guess, try to implement a deep training version of it to a specific instance of a data set or something like that, and try to get pretty high results. Yeah, let me go ahead and read this. Yeah, this is just an introduction to the like setup of the formula. That doesn't really give the answer. This paper is a lot harder to read. Goes a lot in depth. X1 and X2 are conditionally independent given the date label. Words on the page and the words in the hyperlinks are independent of each other when conditioned on the classification of P. Right, it's constructed by a different user than who made the link. Okay, it's just going into more proofs. Ah, jeez. It's a pretty big paper, but it seems to be pretty fundamental into learning how the algorithm really works under the hood. Okay. Let's see. Mostly read this paper, did this, and almost done with that. I think I can call it for today. I'll be back tomorrow to work on multimodal models. All right.